So I want to start by introducing my company, so that this talk is a bit more serious. We are one of the largest marketplaces in Ukraine. We are using PostgreSQL since the start of the company, so it's like 2008, probably version 7, I think. All our infrastructure is self-hosted, so this means that we build a lot of stuff ourselves, host a lot of stuff ourselves, and gained a lot of unpleasant memories about building stuff ourselves over the time. We have a lot of Postgres instances which span across several data centers. So we needed to implement solutions to manage them effectively and and let our users interact with them effectively. We also have kind of large Postgres instances which are Highload, which support a Highload, in my opinion, and are also quite cumbersome to manage. Let's continue. Let's probably, if some of you don't know, I want to just briefly say what is a pgbouncer itself. So it's a database proxy. It works on L7 on the application level. It's single-threaded, which is kind of weird in 2025, but in 2025 a lot of things are weird. It can do load balance on DNS queries, which means that if you have an A record which has several IPs, it will use those IPs for round robining across instances in the cluster. It cannot split read-write queries. It doesn't parse your queries. It only injects its own queries into your connection when it needs to clean up. It can multiplex inbound and outbound connections, which means that it can reuse connections. It's kind of stable and robust, so we are using it a long time, and we had only several problems with it. There are alternatives like pgpool2, for example, which provides almost the same functionality, but even on a more higher level. It can parse queries, it can split across master and replica, but it's kind of slow, and also it doesn't support all the low-level features. There's a pgcat, which is written in Rust, which is multi-core, but kind of Kubernetes alleviates the single core problem. There is a supervisor, which on their page they promise that it's web scale. It can support thousands of connections, but we haven't tested. Why do we even need a DB proxy? As a developer, sometimes as a person who troubleshoots some problems, my opinion is that proxy is the easiest, but the most overhead heavy solution. And proxies turn into single points of failure over time, which means that if proxy doesn't work, nothing works. So you have to, in my opinion, again, you have to avoid proxies as much as possible. But why do we need this proxy? So we can distill the reasons why we need to put the pgbouncer in our infrastructure into probably two. One is we have some high-loaded databases, and we need to control access to our databases and our infrastructure. High-load is the answer to the high-load is the question of the high-load with PostgreSQL is very, very simple. So PostgreSQL implements process per user model, which means every time you connect to a PostgreSQL database, it will spawn a new instance of itself. It will fork, which takes a lot of time. A lot on the scale, and also it means that it will eat some memory. It will need to release this memory, which again is CPU cycles. It is latency, and it's additional load on your database, which is supposed to be processing queries, not just doing some maintenance work. So how does pgbouncer answers this question? We have three models of execution. The simplest, the most standard is a session pool, which means that for each incoming connection, you get one outgoing connection, but those connections which are outgoing from the pgbouncer to the database instance will not be closed and can be reused. They will be closed after some time passes, which is configurable. So this already means that when your application closes the connection, you are not closing the connection on the side of Postgres, you're just cleaning it up, and it can be reused for the next connection, which means that connecting again and reusing the connection is fast. It doesn't incur a lot of latency, a lot of load on the PostgreSQL server. There is a transaction mode, which is more aggressive. It reuses the connection between transactions. So even if your application does not close the connection, it will still, the proxy will still reuse the connection if other application sends some query. So this means that for some number of incoming connections, we will have a lesser number of outgoing connections, even if the connections stay open. And we also have the most aggressive mode, which is a statement pool, which means that for the proxy will use the connections for each individual statement. Even in this mode, probably transactions are impossible, but for some cases it should be viable to use it if you have performance problems. We are using transaction mode mostly, and the session mode when we need maximum consistency with pure Postgres connections. You can say that just to fix this problem, we can just use database connection pool in the application, but I can use this argument to segue into the next part. So if you are using a pool for a service in the current scheme of events, like in the current infrastructure patterns which are built, there are multiple services with multiple pools. Each pool is implemented probably by a different library or in a different language. The numbers of maximum connections on the pools are tuned by a different developer in a large team, and this is very, very hard to control. And you have to troubleshoot problems arising from usage of pools, arising from the fact that you can only limit the maximum connection number on the database, and to change it, you have to restart the database, and otherwise you need to go to the developer and ask him to change the pool size, to tune something, to find why the connections are leaking. And again, we don't want this to become a constant iteration communication between different people. We want to control our infrastructure ourselves. So pgbouncer essentially changes it to the applications without using a pool. They don't use a pool, they just connect to a proxy, and then proxy uses its internal pool with internal values controlled by configuration to connect to a database, which means that you can always change the configuration, you can always see which application, if you're using special query markers, you can always see which applications spawns how many connections to a database, and things like that. So you have absolute control over you are gatekeeping your database essentially. Also, you can with the proxy you can implement the following scenario, which we are using a lot, to split databases, to merge databases, sometimes to migrate between versions of Postgres, and do stuff like that. So, for example, we have a service which connects to a proxy, which can then kind of transparently switch between two database instances. With one is the old one, and then the traffic switches to the new database old one and new can be connected, for example, by a logical replication. In this way, we could split the database without downtime a lot of times. This was very use pattern when we were updating our database version constantly. So if you are already convinced that you need this, I can probably show you a bit of historical info on how we deployed the pgbouncer and what problems we found with it and how we kind of fixed, and how we still live with it. So at the start of our infrastructure, we had the most basic stuff. We had dedicated pgbouncer servers, which were accessible by an application using a load balanced DNS record, again a record with multiple IPs, and then the application would go to one of the pgbouncer servers, and then the pgbouncer server will go to a database server, and it worked for some time until the load became so great that we needed to scale them. And to scale them, we need to set up a new pgbouncer on a new dedicated server. And it was kind of not very effective because it's a single core application, which means that it will only use one core. It doesn't use a lot of memory. So using a whole server for one pgbouncer is redundant. Having multiple pgbouncers on one server is kind of not very stable because they are network heavy applications and they can very quickly exhaust your channel if you are using them for high-load databases.
So yeah, so as I said, we changed the infrastructure so that we had a pgbouncer on every node, which means that we did not have a problem anymore with the. We have no problem with performance, and the scheme kind of worked the way that it worked before. The only problem was that we now have a very, very large pool of connections possible, because we had a lot of nodes, which means each node had an independent pool, and it was kind of hard to manage it. Essentially, it's like an infinite pool. But we lived for some time with this scheme, and then we tried to test a more like another way, where we deployed pgbouncers directly on the database servers. This way simplified pool management a bit, because we knew how many connections can we assign to each pgbouncer, so it doesn't kill a database. But at the same time, this effective, because as I said previously, proxies kind of heavy network application, and database is also heavy network application, and we are having two network applications in one server. It killed Postgres because it was just too it strained the server to the point that Postgres was unresponsive. So yeah, but everything changed. Everything changed when Fire Nation attacked. So everything changed when we finally migrated to Kubernetes, as there was like a huge amount of flexibility on this platform. We could deploy pgbouncers as individual pods, which means they did not have this resource redundancy. We could assign correct limits to them, correct requests. There was a load balancing using Kubernetes service primitive. And it used DNS to balance between the database servers as previously. This scheme is currently used. So I think it's an end of evolution for now, while we are still using Kubernetes. But when we migrated to the Kubernetes, it unlocked kind of a next level of complexity which we could bring to our setup. At first, we had a simple pod with one instance, which means just like a simple application with the configuration. But very soon we encountered the problem, at least it was for our older Kubernetes setup, where the service primitive was not fast enough to drop the pgbouncer IPs, which were terminated. It means that part of the traffic went to IPs which were still unresponsive, which in turn meant that every time we changed the configuration, we had some issues with the database connection, something failed. So we introduced the config watcher, very kind of simple sidecar container, which monitored the file and accessed the pgbouncer using its SQL interface. This is also one of the features that is kind of cool, is that it has like a PSQL interface built in. It's like not real database, but it has a similar semantics. And we could reload the signal a config reload for the pgbouncer proxy when the config changed. And the same happened for example, user lists which are stored in the secrets. So when the secrets changed, we reloaded the proxy. And this means that when we deploy something in GitLab via CI/CD, we can see a log reload command, which means that all the configuration is fresh, everything works. We don't need to restart it. Then we added a metrics exporter because we need to understand what is happening, how many connections do we have, how many clients do we have, what are the problems, observability, etc. Again, it has a very nice interface which can show you everything you need to know about clients, about pools, about DNS even. So you can turn all this interface into Grafana and get all the information for all your database instances from one single page. You can see query time, you can see how many traffic are you receiving, how many clients do you have, and etc. How many transactions, and you can see spikes, which mean problems. We also added a health check because while it is stable and robust, there are problems which happen, for example, with network or with some other parts of infrastructure, which sometimes push it to uncontrollable state. We started experiencing it only lately when we moved to a new infrastructure, probably because something changed. But still, we needed to have some circuit breaking to it. And again, this is done very, very simple. We have a metric which can be extracted from the PSQL interface, which can be a trigger to kind of reload the pod with the pgbouncer, which means breaking all the connections and restarting the pod, and everything starts working again. So this was the same that we were doing manually when we saw those problems. Now it started to happen automatically, which kind of like a self-healing infrastructure. That one of the missing features of pgbouncer that was actually recently resolved was that it used DNS balancing, but it did not health check the IPs of the instances is connected to. So we had to add a proxy, which performed its own health checks and only used the connections to the endpoints which were healthy. A proxy also lived in the pgbouncer containers, in the pgbouncer sidecar. So at the moment we had like 5 sidecars in one pod, which in my opinion is a bit crazy, but it worked. And the pgbouncer was connected locally to this proxy, which was then connected to a database, and proxy was doing the health checks, and this means that only stable connections were used, and everything was kind of fine, except that, and proxy also has this DNS resolver built in, which it uses to build the backend. So you don't need to manually input backends in a proxy config. You can just specify resolver, and it will build it itself, and it will update it, and it's kind of cool stuff. But again, I'm repeating myself a lot, because for me it's a like hard-earned truth is that proxy is a software that turns any traffic into CPU cycles and software queues. So software queues is also CPU cycles, but they're parasitic. They can make your networking slow. They can cause latency spikes. They can cause undefined behavior because it's a network contention in a single machine. So when we introduced a proxy into the pgbouncer pod, what we got is that now in one pod we have 2 proxies. So as you can see, for example, this is one of the servers that one of the Kubernetes servers that has pgbouncer pod in it, and we see that we have busy user CPU at like 46 milliseconds, I think, and busy IRQs is almost the same, which means that if you have a fully loaded pgbouncer instance, we also have a second core only doing IRQs, which is crazy, because now you have on a multi-core machine, this probably is not a problem, but we prefer not to use machines with tens of cores, because the smaller the machine is, the more replaceable it is. So on a machine which has like 8 cores, for example, you have one instance which consumes 2 cores, and it's kind of not sustainable, I think. So now in one pod we have 2 proxies, which both turn incoming and outgoing traffic into CPU cycles and software queues, which again, not a problem, because we could scale them a lot. We could spawn 100 pods of the proxy, but it kind of returns us back to the problem that we have too much proxies, which means it's hard to control the pool, and there are too many connections to a database possible, which means we must constantly fine-tune it, and also it brought some instability into the setup. So every time we wanted a stable database connection, it depended on how loaded the pod is. If it's not loaded, everything was fine. If you had some load spikes, it could break. So we decided to change this a bit. I think this is kind of cool way to solve this problem. Probably it's applicable somewhere else. So pgbouncer uses DNS to find the servers it should connect to. So we can teach pgbouncer to test the health of the database, and then we will have a way to avoid failures if one of our instances fails. And this way we can remove a proxy and add another sidecar instead of it. And this turns our scheme into something like that. So pgbouncer uses our DNS server. So we implemented a DNS server, which is also a health checker. And then pgbouncer uses this DNS server to resolve the addresses of all the live hosts and avoid connecting to dead hosts. Because Unfortunately, it was a very, very much sought after feature, but it was actually implemented and released only in this January, so that pgbouncer avoids connecting to that host. We kind of launch it and it works, and we can see that it, although it has a DNS cache, it resolves periodically databases, updates its IP list, and we see sometimes that there are failures on pings, but it's kind of not a huge problem. So right now we have some plans ongoing for continue some plans to make this even more complex, to add a 6-sidecar. pgbouncer has some logs which could be used to gain more insight into how your clients work, how your database works, but it doesn't have this stuff in metrics. And we plan to implement a log parser to turn those logs into some useful metrics for alerts, notifications, stuff like that. As of now, we can only use metrics like waiting clients, like number of connections, like transaction latency to deduce where is the problem exactly, what is the cause of the problem. But we don't have like a direct metric, a number of errors on a specific database, IP of database or IP of client, because sometimes problems with pgbouncer stem from clients. Clients are slow, clients can hog connections, and we wish to understand who are those clients, why are they doing that. Also, as I said, pgbouncer can work as a circuit breaker if you're health checking a database, but it's not. This check is not 100% complete because it doesn't test for availability of connections. If your proxy, if your database hits max number of connections, Postmaster will only spawn a connection if you have correct credentials. If your credentials are incorrect, and we are using incorrect credentials because we are not providing real database passwords to pgbouncer, we are just going to get an answer, which means that Postgres is kind of ready, and we can try to connect to it. But if you use real credentials, we can check if it has free connections available. And also, as I said that previously, that the feature with health check-in was very much sought after, and they actually implemented it. They've implemented it for 3 years, I think, since 2022, and it was finally released just a bit more than a month ago. This feature allows us to use another balancing strategy with which pgbouncer will count the number of successful connections on host and will reset this number if the connection was unsuccessful, which means it will throw out dead hosts and we will not connect to them, which is also kind of cool and almost makes our own implementation obsolete. So thank you for being with me for so long. This is the picture from Odessa 2021. And if you have any questions, I'm probably ready to answer them.
Дякую тобі, Віталій, за таку шикарну доповідь. Oh, I forget that we should speak English here. Oh, sorry.
English.
Sorry, Vitaly. I will continue English. Thank you for such amazing presentation and for showing us a real use case of using pgbouncer. And there is a question from Konstantin in our Discord channel. Vitaliy, how pgbouncer works with SSL connection? Are there any problems with that?
Yeah, I think there is a support of SSL TLS. As for the problems, I think when I prepared this talk, I reviewed again the release notes, the documentation, and they even fixed. There was a problem that SSL connections terminated and needed to be reestablished, but I think they even fixed that, terminated on reload. So I think the support should be adequate. We are not using SSL between databases, but I mean between the application and the database. But yeah, it's there. It should work, I think.
Okay, thank you. And I have one more tricky question. Just imagine you are starting a new project. You need to fully rewrite prom.ua from scratch. You know all the domain model, all the problems. And in that case, would you choose pgbouncer, or maybe you would go with some other technology stack?
If we are using PostgreSQL, I think it's kind of it's kind of must have in my opinion. But I'm brain damaged by pgbouncer, so I can say otherwise. Like as I said in one of the let me go to this slide. So you have where is this? Yeah. So you have this kind of this problem which arises independently of what stack you have, of what, like if you're having a database somewhere and you're having applications hitting this database, you will arrive to this point at some time. Like you will have multiple services which go God knows where, and you don't know how many connections they use. And if you are in the cloud, you are probably okay because you have money. If you are in self-hosted infrastructure, you have to be a bit modest about this, and you have to have some semblance of control. You can just allow anybody connect anywhere. And also you are going to need at some point to have this clean separation of what are developers responsible for and what are DevOps responsible for. If the developers can just use the infrastructure as is, I mean, this is like a raw infrastructure. If you are accessing database directly, then it's hard for DevOps to control it. Where are they accessing it? How limited is this? That's why even if I would choose another stack for databases explicitly, I would still look at some kind of a proxy to act as a middleman, as a gatekeeper, because databases are like a fragile thing. They are easy to break. That's why you need additional kind of layer. And also it's for even for developers, it's more user friendly to have. So we have in Kubernetes, we have one single database hostname, which is identical for all the applications, for all the configuration files. And for example, when we migrated our infrastructure from Ukrainian data centers to broad data centers, they didn't need even to change the DNS names of the databases, because they are configured essentially in the applications that stayed the same, because we changed everything for them in the background. And it's kind of nice. I think it's kind of cool feature which you get. Yeah.
Yes, it's really good. A good way for developers just to know about maybe not one but two connections, one for write and the other for read, or no? Read or does it have read write host names?
Yeah. We also have this again. We can implement the application in a way that we don't have a database replica at the start if the application is just like releasing, but it already has some read-write separation inside. But then we can just attach a replica on the fly, like application works, and we just spin up another Postgres, replicate it, and switch the read-only connection to read-only Postgres. Application doesn't need to change. It doesn't need to be redeployed or started, tested again, because it doesn't. Nothing changes for the application. Everything changes for infrastructure. That's also kind of
Okay,
cool
I
feature.
get it. Okay, you get it. Thank you for your response. Maybe just to clarify for me. So if we are on AWS and using something like managed service Aurora RDS, they will give us this pgbouncer just under the hood. So you need this only if you're working with databases in Kubernetes on your own. Yes?
In AWS, they are not giving you it under the hood. You actually need to set up it. It's called DB proxy, I think. You are
Yeah.
like setting it up additionally. So you set up an Aurora, even if it's managed, you still can set up a proxy, and it's recommended because again it saves you money in the long run. It saves you memory, it saves you CPU cycles. So it's easier on the database. It's less loaded. There can be some reuse done there. So yeah, and it's kind of like a crutch. Sorry, it's kind of crutch to set up a proxy, but it's kind of leaky abstraction, so that you don't have a just give me a database address, just give me a real instance. But even they use it, even they have it as a product, because it really saves them money in the cloud, and it means that in self-hosted infrastructure, it will at least save you from the need to buy like a new server, maybe, probably.
Yeah, definitely right. It's a good way to optimize your costs and use proxy SQL, as far as I remember. It's called in Aurora. And I cannot see any more questions to you, Vitaliy. So, one more time, many thanks for your time, for your presentation,